Yeah. Can you try if you can share your screen? Yeah.
Trying to join on both my laptop and
Oh, I see.
I just joined with my iPad.
I see.
I should disconnect. Okay, so very low tech privacy. So, oh, I should set this up.
You know,
Oh, thanks.
well, they also have coffee there. Yeah. So, it's not shared on the Zoom.
Yeah, I'm just trying to.
Oh, I see. Here, I see.
I'm trying to get.
Yeah.
Presenter. Okay. Now let's see.
Hey, thank you. So we just testing. I think everything works.
Okay. Okay. Yeah. Now I need to share. Where did Zoom go?
Yeah.
There we go. So okay, this one. And then
Yes. I can see from my computer. I think next maybe we just test a little bit about the, kind of audio. See, yeah, if I see online people can hear from us, maybe you can either type or say something.
hello.
Hello, online people, can you guys hear us?
Yes, we can.
Yes, we can.
Wonderful. Thanks. Yeah.
Great.
Yeah. I think all set up. So yeah. Junjie will make an introduction about you. Yeah, Junjie is here. He will make it.
Okay.
Okay, yeah. Okay. So we wait a little bit, maybe just a couple minutes. Yeah. So, right. Do you want coffee? Or have coffee there?
Oh no.
So, so how do I spell that's, I mean,
In a way.
no, yeah, no, thank you, yeah, thank you very much. Yeah.
Sure.
It is a second year or third year?
Actually beginning my fourth year.
Oh, yes, a little 1 year earlier than we are.
Yes. Yeah.
I see.
Just 1 year. Yeah.
Yeah, this is my second year, start the second year. I joined last year.
Okay.
I mean, industrial engineering.
Oh, okay. Okay. Nice. Nice. Yeah,
Then 2 years. Yeah, I was also 2 years, right?
how's it going?
It's good. Yeah. Everything's good. That's it.
Everything's good.
One class did teach for this semester. One class.
There's one comment, but it has that's AI.
I see. 200. 250.
I've never taught a small class before.
That's it.
So for better or for worse.
Yeah, that's a lot of people. Oh, all right. Maybe we can get started. So, hello everyone. Welcome to our ICON weekly seminar. Welcome student. Welcome participant here, and also welcome participant online. And I'm Yu. I'm one of the co-organizer for the event for the seminar. So I'm assistant professor from industrial engineering. I work on robotics, robotic manipulation, software robotics. Today is our honor to have our speaker David Inouye. Sorry for that. David Inouye, he's from electrical engineering, ECE, Purdue University. So he leads the probabilistic and understandable machine learning lab, which focus on fundamentals of distribution alignment, probabilistic models, and explainable AI. More recently, he's interested in distribution alignment, including new alignment of algorithms, measures, and applications, such as causality and domain generalization. So on the explainable AI side, he is interested in distribution, shifter explanations, and the tractable uncertainty quantification. So previously, he did his postdoc at the CMU, and he received his PhD at the University of Texas, Austin in computer science. So let's welcome Dr. David Inouye. Yeah, the floor is yours.
Thank you. Thank you so much for having me. I'm excited to talk today a little bit about it's kind of a high level talk on this idea of distribution alignment. And if you don't know what that is, hopefully by the end of this, you'll know what it is and possibly know why it's useful. And so that's kind of what talk's going to be about. So just to start things off, standard, machine learning tends to assume that kind of all data is relevant. It's just kind of, give me everything. What if there's bias or spurious correlations or all sorts of things that could happen? And machine learning is just like, I'll figure it out. Right? You just give me a bunch of data. I train my model. I'll figure it out. So it kind of assumes that all data that you're giving it is going to somehow be relevant. But what if some of the data is actually assumed or designed to be irrelevant? So for example, in fair learning, you might have some sensitive attributes like race or gender that are designed to be irrelevant for some social applications. You don't want to necessarily use that information to make decisions about loan, either because of laws or fairness, these types of things, right? So this is, by design, we want this information to be irrelevant to our predictions. Robust learning is another case. If you look at these domain adversarial neural networks or invariant risk minimization, this domain where the images come from, say they come from Norway, or they come from France, or they come from Belgium, they're all wheat images, right? So where in what country and stuff, you might, in this case, you're counting, say, the number of heads of wheat. And so that task should be invariant, shouldn't matter where you took the images, right? So it's assumed that this information is kind of irrelevant. A human should be able to look at these and count the heads of wheat, no matter which type of image, which place it's being taken from. So these are called different domains. And so that's one of these ideas. So another time when data is assumed or designed to be irrelevant. So another case is unsupervised image-to-image translation. So then the source of images, whether it's real or generated, right? That's kind of a flag, is designed to be irrelevant. So you shouldn't be able to tell whether it's a generated image or a real image. Okay, so that's, again, another case in which we kind of, by design, create a generated image and compare it to a set of real images. One other case that we'll get to in a little bit more in depth later is for causal discovery. So interventions are assumed to be irrelevant to most of the causal mechanisms. So what this means is one natural way to think about interventions is that you're only changing kind of one variable. You're trying to keep all the other mechanisms. So you can think of a physics experiment. When you want to see something, whether it's causal or not, you're only going to intervene on one variable. All the other mechanisms, all the other physical aspects of the system are going to behave in the same way, right? And so you can think of different types of intervention. The one on the left might be more of a physics type of intervention. The one on the right might be, more like an image type of intervention. If you take all pictures when there's no lights on, or you turn all the lights on, it's going to be a different set of images you'll get. Okay, so the idea is that, again, that these interventions don't affect all of the causal mechanisms, they only affect some of them. So this leads to the question of how can known irrelevant information be used? So suppose you know this, you have these domain labels, you have certain information. How can this be used? You have gender and race, these types of information. How do we can we use that? So one idea is to simply discard the irrelevant features, right? This might be the most obvious thing you think about, kind of naive way. But this has problems because even if you remove like the feature gender, that can be somehow encoded, say, in the applicant's name. So applicant's name, there's going to be female names and male names. And so you can actually infer often the gender from the name. So you can't just drop that feature. So people realize this pretty early on in the fairness literature. You can't just drop that feature and just act like it's not there because there's kind of other stuff encoded. So you actually want something stronger. The other problem is these irrelevant features may be unknown. Like they exist, but you don't really know they're somehow entangled with the relevant features that you care about, right? So that might not be in the end a final good solution. Another way is to think about model design. So how do you handle this irrelevant information? You can hope that the model implicitly ignores irrelevant information. And in some ways, I think of lots of architecture type improvements for neural networks are basically based on this assumption that you just kind of hope the architecture ignores certain irrelevant information. So use a convolutional neural network instead of linear and things like that. I mean, instead of like kind of fully connected. So you could also design the model to explicitly ignore this information, but you usually can only do this for something that's easy to formalize. So if you can mathematically formalize what irrelevant means, so for example, you might be able to say an image that's flipped left to right or right to left should have kind of the same type of properties. So the people have worked on these types of invariances or equivariances. So you could do that if you can really define exactly mathematically what it is. And you might have this, you know, in physics, you might have certain permutation groups or something. So if you can define how, like, okay, these things are the same type of thing, maybe on graphs, you know, you permute the nodes and it doesn't give you another graph. So you want some equivariance across node permutations. Those are all kind of, you could do by design in the model, possibly. I suggest, what this talks about, distribution alignment is another way to handle and to accommodate for this, you know, known irrelevant information by explicitly minimizing this irrelevant information, even if it's informal, if it's infeasible to formalize. So you can't kind of write down mathematically what this invariance is going to look like. Just like I kind of think of this as, you know, classification, right? Very hard to write down what a cat is or dog is, but you can get labels. We can train something to learn what a cat and dog is from examples. Similarly, here we might have the domains, but it's not like I can describe what's the difference between wheat images in Belgium versus wheat images in France. I just know they're different. And so how can I kind of leverage this kind of the simplicity of domain labels, possibly to get more robust models to, you know, do things. Okay. Any questions so far? Okay. Yes.
Is there general features for those, you know, irrelevant features, or is there any like general features? How do you define, say, what is the cost function, or what's how do you have any features about those irrelevant information?
Do I have any? Are you saying how do you define irrelevant information?
Yeah. Because you cannot do a classification when you find out what is the irrelevant information, right? Do they have some like a common features across different types of objects? Yeah.
Maybe I don't know if I'm understanding your question, but I'm thinking maybe you're asking kind of like how do you define, how do you choose domain labels, for example, or.
Yeah, maybe I'll ask later.
Okay. Sure. Yeah, maybe hopefully it'll become more clear. Because that was, of course, very high level and a bit hand wavy of what irrelevant means and things like that. So this is my one slide attempt to make the site to kind of give a sense for what distribution alignment actually is. It is the opposite of. It has the opposite objective of classification, basically. So I think of distribution alignment as learning a representation function G. So G in this simple case goes from 2D space to 1D. And you can think of classification as finding a representation that maximizes the distance between the two classes, right? So it finds, in this case, I'm just thinking of simple rotations, basically, and then a projection, projection onto one-dimensional space. So classification, the best classifier direction, so the best way to modify X such that the distribution, the blue distribution, is far away from the red distribution. This is actually what classification is doing there on the right. So you can, right now, I'm kind of just assuming that this phi is some sort of divergence between distributions. You can use Jensen, Shannon, KL, Wasserstein. I'm not saying you can use any of those here. So it's just kind of, this is in some ways just a different viewpoint of classification. Distribution alignment, the big difference is now you're minimizing this divergence. So you're trying to find a representation G. Again, we're still going from 2D to 1D. You're trying to find a representation that minimizes this divergence. So now if you rotate the other way, you can get a case where the marginals that are aligned, the blue and the red, overlap with each other in distribution. right? And the optimal solution is when they're actually equal. If you can fully minimize it, right? Then when divergence is 0, then these are equal. So that's the high level way I like to kind of describe this concept. I'll again get into a little more detail later, but I hope this is any questions on this slide, because this is pretty important.
Just want to make sure that if we have that optimal solution there, that means there is no bias in terms of B for all of the distributions.
So you ask if on the bottom there's no bias, as in like if you were doing fair learning, is that what you're saying?
Yeah, there is no bias in terms of like B.
Right. Yeah. That's a good question. Yes.
Because otherwise it's just a section.
Right. Exactly. Yeah. So it's a great question. So yes, the answer is yes. All of them are going to need some constraint on G, because otherwise we end up with these trivial solutions. Kind of like autoencoders, right? If you don't put any constraint on autoencoders, they just find the identity. But the similar thing here, if you don't put kind of any constraint, one simple constraint, for example, is to make G invertible. Or you could approximately invert it with an autoencoder type thing. But if you make G invertible, then you can't do certain kinds of things. But yes, we eventually will definitely need some sort of constraints on G to make this an interesting problem.
David,
Yes.
so some people ask question online, did you prefer XML? Maybe
I think if they're on this, then it's probably useful to answer them now.
yeah. So Wang is asking, is this almost the same as optimal transport?
Is it almost the same as optimal transport? Good question. So in many ways, this bottom part, this is the constraint often in optimal transport. So in some ways, all distribution alignment, so optimal transport is find the mapping that has minimal cost such that these two distributions are equal. So actually, the constraint's the really hard part of optimal transport. Like anybody can compute, squared norm of some representation function, but enforcing this constraint is very hard in optimal transport. So either we have discrete algorithms for optimal transport or things like that. So if you so this is in some ways you can think of this as a way of implementing that constraint in optimal transport in kind of a more general way. It's a great question. And so, obviously, if you have kind of if you're doing joint alignment, then one, optimal G could be the optimal transport solution. But there are other alignment solutions. But of course, that would be one possible. So there's definitely relationships to optimal transport. But in some ways, I'm just saying this is only trying to kind of enforce the constraint part of optimal transport, not necessarily finding the optimal map. But as we'll see, in applications, basically, you usually need something you want, and this is the stuff you don't want. So this is, the application objectives say classification is the thing you want, the positive, and this will be a constraint, kind of the negative. So you don't often use this kind of by itself directly. It's another great question. Okay, so we're still in the concepts here. So you can think of there being different types of alignment. On the top, we have marginal alignment. So you're able to align a marginal, but not necessarily the joint distribution isn't aligned, but a marginal is aligned. We have, conditional alignments. This is where I'll give another example of this in a second, but the conditional distributions in this case kind of lie along this, simple function of V2 given Z1. So this was before align, on the left, we have before alignment. On the right, we have after the alignment. So you can do conditional alignment. And then, of course, there's kind of joint alignment. And yeah, to get to that other question, this joint alignment, one solution to this is optimal transport. One G that works for this kind of alignment is the optimal transport G. Now let me get to, this might be still a little confusing. So here's a case in which you can get, and right here, I'm just looking at very simple rotations of the original distribution. Okay, so you can think of this left side as kind of the original distribution. And I'm trying to learn a rotation such that maybe the marginals align. So on the top we have marginals, bottom we have conditionals, and in the middle we have joint. So what I'm saying, of course, is here, if in this case, the marginal is not aligned, and neither are any of the conditionals, right? None of these conditionals are aligned. Okay. On this side, we have the marginal is the same, but the conditionals are definitely all the conditionals. So when you do conditional alignment, you would want to align all of these conditional distributions, for every slice in some sense. Now here's another slightly more complicated example, right? You can have, this may be the distribution you originally see on the left. And some rotation of that gives you, again, where the marginals align. So it can be, it can obviously be a more complicated distribution. So you get marginal alignment, even though the conditionals, right, the conditionals are lying on two different lines, right? Possibly just by a shift. Now, these, of course, are constructed examples. These are not real data, but trying to show these concepts kind of visually. And then here is conditional alignment without marginal alignment. So, suppose this left was your original distribution, right? So you have this kind of sine wave, rotated sine wave type of thing, much more complicated distribution. Again, in certain rotations, the conditionals are not going to align. But in this case, we have that the conditionals align. So every conditional slice, the red and the blue, so this is going to be that P of Z2 given Z1 from one domain is equal to P of Z2 given Z1 from domain 2. But the marginals, P of Z1 from domain 1 is not equal to P of Z1 from domain 2. Right. Right. Yes. Yeah. You can kind of think of this as the original X, and we're trying to learn some rotation. In this case, very simple, right? Some rotation such that you get conditional alignment. So hopefully that's gives some of the intuition of what is conditional alignment. I think is actually one that is not really well studied yet. I feel like people know marginal and joint alignment, but this conditional alignment where the margin, one of the marginals doesn't align is something I think that a bit understudied. So here's just to give the kind of more full definition of what this is my attempt at a definition of what this is, because I do think people like want to use it sometimes and then use it, but they don't define what they mean by it sometimes. And so I'm partially through this work trying to kind of give the right terminology to things. So joint distribution alignment means that you have some samples from a joint distribution of X and D, which D is the domain label. So we're trying to find an aligner G that minimizes some divergence between these two distributions. Right. and you can use any sort of divergence there in phi. So it's a representation learning problem. That's how, at least how I'm phrasing it. It's a representation learning problem. And of course, where z is some function of x and can possibly depend on d, the domain label. Now so this is kind of hopefully a high level framework that incorporates all sorts of alignments. Sometimes the G is shared based on your context, where D is not dependent on D. But other times you have one transformation for, say, the male applicants and one transformation for the female applicants so that they can align. So then it will depend on D. The conditional distribution alignment, I think, is a little bit more complex. We have, two variable sets. You have to aggregate, so we need some sort of aggregator because, right, there's a conditional distribution for every possible ZB, right? So we need some way to aggregate the top one, right? There's no, but this one at the bottom, we're saying we want all the conditionals to have a low divergence, and we need some way to aggregate over the set of ZBs, the vectors in ZB. One kind of standard prop one is probably just taking the expectation over the marginal of P of ZB. So that's, I would say, probably the most natural choice. But in theory, you could use something like a max or, some other aggregator. So it's a little different because you have multiple conditional distributions you're trying to align in that sense and weighting.
So for these definitions, you still haven't ruled out the variable by constant solution. So the constraint that we talk about, for example, you have for set a linear transformation, maybe there's a graph function that you are not using out all information.
Yeah. Yeah, so far I haven't put any constraints on G. That's, but it's, well, actually, I don't know if I'll cover that yet. But yeah, that we should talk more if you want, because it's definitely interesting to see what kind of constraints are useful. So so like if you think of let's say the unsupervised image to image translation, the constraint there is one of them is the identity mapping. So like in some senses, domain one, the real samples, G of XD is just the identity. And then for G of XD equals 2, that's going to be the generator. So if you constrain that, then you can't, once you have one of them fixed, like one of the domains fixed, then you can't map everything to a point. So that's another example when it's, then you can allow G to be kind of arbitrary like in GANs, but you don't have to. Yeah. So here's just putting these things into this as framework. We have a shared aligner. It doesn't depend on D. It's I apply it to the blue and the red exactly the same, right? So this is a shared aligner. And my conditioning, in this case, I'm only aligning the marginal. So my the conditioning set is empty. Think of this as marginal alignment. On the conditional alignment, now you can look at this as I'm fixing one of them, as I was just saying. You can kind of fix the D equals 1 G part to just be the identity. So that's a constraint. And then this other one, I'm just in some sense training this A parameter, right, to see how to make them align. Obviously, this is a very simple case, but this is the conditional alignment. And then this joint alignment, again, I'm fixing the second part to have an identity function and then essentially learning this G tilde function for the other domain to map it. And G tilde here, again, could be that optimal transport map. There are many other possible maps, but that's one. Okay. So now on to It's trying to give some of the main concepts. Now we're on to how do you measure this? So we obviously need to be able to evaluate, and actually evaluation is hard. We want to be able to evaluate to compare alignment methods and possibly to design objectives because we want to minimize some alignment measure. So we want to say how close are two distributions. You might think, oh, let's just use theoretical divergences. That's great. KL, Jets, Chan, TV. Most of these are intractable to estimate though, given only samples. So we're going to focus on this talk on some tractable or approximation to alignment measures that you can actually compute. Extrinsic, I'm going to categorize these as extrinsic alignment measures. They're not directly measuring alignment, but they're measuring something around alignment. So there's one common case is to use an external task metric. So in fair classification, for example, you're going to measure, the accuracy of your classifier as well as maybe some fairness metric. And so even though you're using alignment, you're not directly going to evaluate alignment. You're going to evaluate these external task metrics. Another case, you might do this for domain generalization. You might say, what's my generalization performance on a new unseen domain? I'm going to use alignment as part of my overall method, but I'm not going to directly estimate alignment, like, evaluate my alignment. So it does not measure alignment explicitly. And then you have, in the GAN literature, these are the most common type of Frechet inception distance or inception score. It's evaluating the perceptual quality of images based on some network. Tries to estimate both quality and diversity. But if you have, say, if we're trying to think of more general alignment concepts, then you can't use this kind of metric in, like, if you don't have much data, then you can't train a model that has good latent space. You don't even know if the latent space is good. Like, we know images really well, so we're like reasonably confident the inception V3 network has a good latent space. But how do you know that? You're working in physics or something, and how do you determine whether something is good or not? And is perceptual quality what you care about in a lot of domains? Probably not, right? So perceptual quality is obviously useful when you're trying to do creative stuff, but not necessarily if you're trying to do science or something. So intrinsic measures, the most common one is adversarial measures. So you're going to implement kind of an adversarial type of measure that can be written as a maximization problem over some discriminator F. Here I just showed kind of the standard GAN. And this is going to be, related to Jensen-Chandler divergence. It's a lower bound. Difficult for training, I would say. This is, if you've ever tried to actually, it's all very nice in theory. You actually try to implement one of these, and it's very hard. People have gotten it to work. Don't get me wrong. I think there's really some nice things about it. It just can be very hard. And it's rarely used for evaluation. So people almost never use this objective to say my method's better than your method. They don't use this because it's actually not a good approximator to the Jensen-Chandler divergence directly. It can be useful for training basically, but not useful for evaluation. There's some other measures based on Wasserstein distance. So you could use empirical optimal transport algorithms if you have just some samples. That's going to scale quadratically in the number of samples. If you have 1 million samples, it might not be feasible. Also in higher dimensions, if you use a small number of samples, it might not be a good estimate. I actually like slice Wasserstein distance. There is some closed form solution in 1D. So these are some other possible interesting directions to think about that are not this kind of directly this adversarial term. So one attempt to fill this gap is something we proposed called the alignment upper bound. And is particularly useful when you have to constrain yourself to invertible G's in this case. But you can do this here. So we form this variational upper bound on the density chain of divergence. Instead of being a max over something, it's going to be a minimization over a density Q. And you can see that it's essentially like a normalizing flow log likelihood with a shared Q distribution. So the Q density model here is shared across all of the domains, whereas each G could be different for each of the domains. So this is a constraint on G to be invertible. We prove that the bound gap is exactly this KL divergence, basically essentially a mixture. Actually, there should probably be this should actually have P of D equals J in here, but it's basically a mixture, the KL divergence between the mixture and your Q density function, your kind of variational density function. So it has some similarities to kind of elbow, like it's going to be, the gap is exactly this KL term. And otherwise, it's going to provide this upper bound. And so it leads to this problem that's cooperative, where you do now minimization over G. Now this phi is no longer a max over something, it's a min over something. So you get this kind of cooperative optimization problem. So, and we also show that in theory, as long as G is kind of infinitely expressible, which may or may not be true, but supposing it is, then you don't actually have to constrain Q too much. It'll do alignment. Now, there is some trade-off of how expressive do you make your Q distributions versus how expressive do you make G, and we don't fully understand that. So there's a lot still going here. So this work was accepted in NeurIPS this year. And I'll go a little bit more on. This is the measure part, and we'll get to the algorithm in a second. So we covered alignment concepts. Oops. Alignment concepts, alignment measures. Now we're going into algorithms. So how do you actually do alignment? So obvious case is to take some of those measures, those tractable measures, and minimize those. Adversarial optimization is exactly that. It has this intuition that it's this competitive game. Someone's trying to counterfeit. The police is trying to catch them. So this discriminator is like the police, and the generator is like a counterfeiter. So you're going to try to counterfeit the real data, essentially. And most commonly, people just use an alternating, do a small update on the min, do a small update on max, and go back and forth. The really nice thing, so one of the big problems with the measure I just introduced is that I said it had to be invertible. This is the G. In this case, you don't really have any direct constraints on the generator or the discriminator. So that makes it a lot more flexible. You can use kind of any arbitrary architecture. But as we talked about, it kind of lacks these domain agnostic evaluation metrics. So we can't, how do you know if it's overfitting? Look at some images and see, like there's not really a good way to check whether it's like doing something really bad. And sometimes, again, the adversarial optimization can be unstable and hard to train. So if we use that as I hinted at, we can do minimize over our alignment upper bound. And you can think of this as in some ways, maybe this is a nice illustration. So it's kind of, the Q is kind of trying to match the mixture of the blue and the green. So the Q distribution could be seen as trying to match the mixture, right? We know that's the gap between the bound is the difference between Q and the mixture of the two different distributions in blue and green here. And simultaneously, so that's what this min over Q is. Now the representation is trying to maximize its likelihood under Q, and so it's trying to spread out. So in some senses, the G is trying to push the PZ1 and PZ2 out to match Q. So obviously, if they push PZ1 becomes Q and PZ2 becomes Q, then obviously they're one. Right. So that's what this kind of the intuition of this min-min optimization. Okay. Oops. So we actually showed that, some of the results is that these are 4 tabular data sets. So how do you check alignment in tabular data sets? It's kind of hard to know. But if we use this, we actually have a measure. So we can do tests AUB scores essentially, is what we have here. So when there's not that, French interception distance or something like that, we can now use this measure. And then here is kind of a translation. So that's just another demo kind of translating digits. The left one is kind of the baseline and ours is the right. So I guess the main thing to emphasize on the right side here is just that we can also do it kind of between multiple domains at the same time. So this is 10 domains, treating each digit as a domain. Then we can translate between 10 different domains. So most like align flow, one of the baselines, and this LMRF, these are 2 invertible baselines basically that we were mainly comparing against. And they're not really built to be able to do the multiple domain thing. Okay. So another work is called iterative alignment flows. So this iteratively solves one-dimensional problems. So this is where the Wasserstein distance comes into play. So we first solve this max slice Wasserstein distance. So we find a theta that I project my data onto this one-dimensional space, right? And then compute the Wasserstein distance along that space. So this is called max slice Wasserstein distance. So first we need to solve this. Not necessarily easy, but there are ways to try to approximate it. Actually working with Matt on better ways to approximate this max slice Wasserstein distance. And then in closed form, we can map along this one-dimensional case. There's a lot of optimal transport stuff that says you can actually compute the barycenter in closed form and map to the barycenter in closed form in the one-dimensional space. So you do that. Then we just update kind of our global aligner with this new layer, and we repeat. You can think of it as pulling off the residual. So each time you find the biggest misalignment, then you align it. And then you find the next biggest misalignment and you align it, and keep doing this. So it's kind of like a residual learning type of idea. And one of the main benefits is that you can actually get one, it's fairly simple. It's kind of a greedy, simple algorithm to build up this deep model. It can be significantly faster in terms of training as far as you're going forward. So alignment applications. This is kind of the last thing, trying to pull some of this together. And again, this is where I'm making a take on this about what I think alignment really should be useful for. I don't think this, feel free to critique. But I kind of think of it as 2 main things. One, again, you have this task objective that I think of as the positive, the relevant information that you're interested in. And I think of alignment constraints as kind of the negative, the thing you don't want, something about irrelevant information. So I think of all alignment applications could kind of be formalized under one thing is the task objective and one thing is the alignment constraints. This is my attempt to unify. That's part of the title. This is another attempt on this part to unify previous alignment applications. So you have this in fair classification. So what you want is to classify correctly, but you want to control, that's going to be your negative, This will be your positive, right? So we want to accurately predict. So we can just use a standard classification loss here. But then we're going to try to make it so that the distributions overlap, right? So we align, that's our constraint. We want it to be kind of independent of some sort of sensitive attribute after aligning. Okay. So this is a nice figure from this fair normalizing flows. You take some distribution here, you want to map it to something that has the distributions overlapped. And for there, you can still do classification, hopefully. So that's the idea here, is that we can do classification in both spaces well. But in one space, you can easily tell, say, you can determine the sensitive attribute, and the other space, you can't, because it's now aligned. The two distributions are aligned. Unsupervised image-to-image translation. Again, we have what you want. I think it's actually a little bit implicit what you want. So I don't feel like they really formalize it, but I think they really want to preserve the image content somehow. Which is somewhat vaguely defined, but they want, right, when they do this translation, the idea is they want it to look like the same painting. They want to somehow preserve that. And they use various things here, cycle consistency, identity regularization. That means I don't want it to, the image diverge too much from its original image. I think they're, using convolutional neural networks is just an implicit way of kind of encoding what you want, which is you're more interested almost in texture kind of things rather than the bigger structure of the image. So convolutional neural networks, I think, tend to have that implicit bias. And then here's what you don't want. You don't want to change, or you want to remove kind of the style. So you want to make it look like the other. And that's, again, here we have the simple case where, right, we fix one distribution and we try to generate the other. So this is the translation, and this is like kind of the real. So we want to align these two distributions. Now for one of my last ones, I'm going to have to, maybe this is, Murat probably could explain this way better, but if you weren't here, I'm going to try to do a very small intro to causal discovery for this last application. So this is my, again, perhaps poor attempt at causal discovery explanation. So there's these two variables, stove on, boiling water, let's call them. And you have the arrow going one way versus the arrow going the other way, right? Now, these both imply conditional factorization of the model, right? One is where the P stove and then P boiling given stove. These, you could just use conditional chain rule. Either one of these are valid as far as the joint distribution, right? But which factorization is causal is question. Even though they're both, kind of reasonable factorizations of the joint distribution. And my suggestion is the one that encodes this effective intervention. So if I intervene, if this is the correct thing, I intervene and I say, force the water to boil. I get a new distribution. I force the boiling to be true, so that's just a delta function on boiling is true. You can think about. Now, in the real world, though, forcing the water to be boiling to be true doesn't change my distribution where the stove was on. I can shoot a laser into my water, force it to boil. That doesn't mean it's going to turn on the stove, right? So my stove distribution, in some senses, won't change. But on the other case, if I force the boiling to be true, right, then this would change. So in this case, the these will be different, but this one will be the same. So these are going to be aligned, as in after intervention, these two distributions are aligned. Whereas after intervention, again, we intervened on this one, so that obviously these are going to be different. But then the probability of stove given boiling is actually going to change, because it's just going to be equal to the original distribution of P stove, right? It's no longer going to have this conditional distribution when I intervene. You can similarly do the opposite side. So what if I force the stove to be on? Then we have a similar case again, where this distribution stays the same under that intervention. So now if I turn all the stoves on, a lot more water will be boiling, right? You know, suppose this is in everybody's house, whether stove is on versus water boiling. But that, you know, the incorrect causal factorization will, again, cause these distributions to be different. Okay. So again, both of these on the left could be reasonable ways to factorize the distribution, but one kind of aligns with causal ideas and one will not under interventions. So interventions is very important for causality. Now let's look at different domains. So each domain is going to can be viewed as an unknown. So we don't, you know, if you have these wheat images, right, you can't exactly specify what's different. So they're unknown. We don't really know kind of what we intervened on per se. And it's probably in some latent causal space. So there's maybe some causal, right? Maybe on the right, you have, it's darker and, you know, maybe the images are taken with a different kind of camera. And those are some interventions that might happen between different domains. There's different kind of interventions in the latent space, but then the actual observed data that you see is going to be possibly entangled and stuff like that. On the top, it's kind of disentangled. On the bottom, it'll be entangled. So that's why like all the pixels on the far right are like darker than all the pixels on the left. Even though there's only maybe a few small things that have kind of changed on a semantic level. And one of the big assumptions that we'll end up having is that basically when you do an intervention, so here's an intervention, it's saying that this distribution, the conditional distribution of Z2 given Z1 is going to be different than this distribution. So these are going to be different under intervention. But, right, this is going to be the same distribution as this distribution. This distribution is going to be the same as this distribution. This distribution is going to be the same, right? The conditional distributions of the others are going to stay aligned. In some sense, they're going to be equal. So only one of the conditional distributions is kind of misaligned under a sparse intervention in this case, only intervening on one node. All the rest of the conditional distributions should stay the same. Same thing over here on the right. Again, we have that, you know, all of these distributions and this. This distribution, all of these are going to be the same. There's only going to be one, this marginal distribution here of Z1 that's going to be different between intervened and non-intervened. So this is what we have for latent causal learning. We're actually going to now have this task objective. So remember, we have the task objective plus a constraint. So we might want to essentially learn this latent causal probabilistic model. Maybe we'll minimize some sort of log likelihood to find this model, this causal. This is going to be on latent space. So we want to find a causal model in the latent space. And what is our constraint going to be? this idea that the difference between these distributions should be sparse in the latent space. So this is a fairly complicated alignment constraint. Sparse conditional alignment, it means that, let's for simplicity just say this is 0. So the times that these are misaligned, it's going to be small. They're the intervention set. We're going to say this is the intervention set. It's the conditionals that are misaligned. Right? They have a divergence greater than 0. So they're going to be 2 different distributions. And I'm going to call this I hat as an estimate of the intervention set. And then I'm going to make sure that this is small. Let's say 1. Right? So the number of intervened conditionals is small. That's going to be one of our big assumptions. And this is actually ongoing work with Professor Kajolu and one of my students. And we're still trying to figure out how to implement this constraint. It's a very kind of weird and complicated constraint. Maybe not weird, but it's not non-trivial for sure to implement this. Also try and understand, does this actually get us at something causal? What kind of this constraint will remove certain possible representation functions, right? It's going to constrain the space of representation functions because it has to be less than k. If k was equal to d, then you could just use the identity, and everything can affect, the domain can kind of affect every pixel, right? But if you enforce this, you're saying one latent variable or only a couple latent variables can change their conditional distribution, as opposed to like all of them changing between domains. So maybe to give a concrete example, right? Misalignment sparsity in 2 dimensions would say that you can either have the marginals be misaligned, one of them has to be aligned essentially. If nothing is aligned, then it's like the domain, the intervention kind of hit both variables. It affected both variables. So that would be kind of a non-sparse, neither the marginal nor the conditionals are aligned. But then on the right, you say, okay, one of them is aligned and one of them is misaligned. So this is if k equals 1, dimension is 2. You're saying I want to find a representation where at least either the marginals or the conditionals are aligned. And more generally, if 2 joint distributions are different and you use an invertible G, then there's no way that you can get everything to align, that they would be equal. So you can get sparse alignment on subconditionals, even though the joint distributions are very different possible. For domain generalization, the main idea is similar as far as the alignment constraint. The main idea is if you could get the causal parents and you only use the causal parents, then you could actually predict Y well under distribution shifts and things like that. But learning these latent causal parents is very hard. So we're first going to try to learn those latent causal parents. So we need to learn that representation function. Again, so once you have that representation function, it's kind of easy to do some other stuff on top of that. But learning that latent representation from like a causal perspective is very challenging. So just long-term future vision, I view alignment as possibly a way to combat underspecification in deep learning. So this is a nice paper by a bunch of people at Google, where they show that even though on the left here, your ImageNet test accuracy, right? So kind of your generalization on the test performance is very similar. Even using just different random seeds, your performance on different perturbations is going to be very different. So just using different random seeds can all have the same test error, but will be very different when you have small distribution shifts. You should have 4 different kind of image shifts. Some of the models happen to be better, some of them don't. So there's this huge set of equivalent models that all have the same test error. And so we actually need more constraints, I think. We need appropriate and flexible constraints. And I think alignment, it might be one way to get at more flexible and appropriate constraints that are relatively easy to encode using domain labels as far as the human effort. They don't have to, formally write out the invariants they want or something like that. They can just give you domain labels. Yeah, and I'll just point out that I do think there's kind of future directions in kind of all of these 4 different areas. And I think I'll just end there. This is 3. Sorry.
Do you have any questions?
So when you propose metric to measure maybe difference between 2 distributions, you require that metric be differentiable with respect to your 2 functions or maybe some parameters that parameters.
Do you, so that does the divergence need to be differentiable with respect to G? Yes. Well, slight caveat. So if you want to use the measure to learn the aligner, then yes, you're going to probably need it to be. But if you're just trying to evaluate your alignment, then maybe not. That's why you can still use like empirical optimal transport for something like measurement, maybe, but maybe it's not always. So yeah, simple answer is I'd be okay if you gave me a measure that wasn't differentiable, but that you could at least check, whether something was aligned or not. But in practice, we often want to minimize it directly. So. Question. Yes.
What if D is a continuous random variable? How does all this?
Ah, a great question. So so the domain label is somehow kind of continuous.
Income you want to hide because you have states.
Ah, yes. So people online, the question is, what if D is continuous, say like income, where you want to hide the effective income, say, to be fair. I think all of the theory works. Just letting D be, D could even be a vector. It doesn't have to be, a single thing, categorical thing. I think like all of the definitions work out as far as like that you could define an aligner that is invariant with respect to a continuous D. I don't know how many people have done that, even with like GANs. I don't know how many people have there. I've seen a little bit like a regressor GAN, maybe. And I think people assume that the only way to do alignment is adversarial. So they kind of conflate the method of adversarial with alignment, because it was actually the only, like one of the only methods to do alignment. And so we're hoping to be more general on that, but that's a great question. I think one of my projects I'm trying to do that, but I don't know if we figured it out. Maybe you could bring out a alignment with continuous value. It's also hard to explain, so I just try to stick with class, for the high level. But a great question.
You have more questions here? Let's see if we have question online. Do you have question online? I think they're good. So then let's thank our speaker David again.